Okay, hello guys. This is Rico, and I'm gonna be discussing a paper 5 question. And as best as I can, I'm going to discuss this as if I'm doing the paper for real, and I'll be showing my thought processes throughout the video. So we're gonna do this whole paper, and without further ado, I think we can start. So the first question is about molar volume. Molar volume is basically gonna be the mass over density. So you know how hello guys, this is Rico, and I'll be discussing a paper 5 question from May June of 2022. I'll be showing my thought processes throughout the whole paper, and as much as possible I'll be trying to do this paper as if I'm actually doing it for an exam. So without further ado, I think we can get started. The first question is going to be related to planning an experiment. So basically the student is trying to make an experiment which finds the molar volume of hydrogen gas. Molar volume is really just you can use the definition of mass in order to find molar volume. So molar mass times density, which is mass molar mass is gonna be density times volume. So this is going to be the density of our substance, and it's going to be the volume of our substance as well. So molar volume is just going to be our molar mass over our density. That's what the experiment is trying to determine. So the student has the following materials. I think everything here is quite normal. I don't think there's anything which really stands out. Except maybe this, a water trough. Basically what our water trough is basically just a sort of basin, a really big basin for water. Other than that, I think everything here in the equipment should be something that we are familiar with. So this is the student's procedure. We're just gonna briefly go through this so that we can get an idea of where the experiment is going. So basically the student prepares a magnesium ribbon. They have hydrochloric acid, and they're gonna pour it into a conical flask. The conical flask is going to be attached to a collection system, so hydrogen gas is going to be collected. Then the experiment starts. So that was the preparation. The magnesium ribbon is going to be in the flask. The flask is going to have a stopper to stop any gas from escaping it. So we're going to wait until the final volume of gas is constant. Basically what that means is no more visible reactions for us, or no more changes in the system. Here the student waits just to be very sure the reaction stops, and then they're going to measure the final volume. Okay, I think we could discuss the first question at this point. So basically it's asking us to fill up this diagram of sorts. So basically this is our magnesium ribbon, and we're supposed to demonstrate how the gas is going to be collected and measured. So this actually requires some information from our IGCSE. So you may or may not remember, but in the first units of IGCSE chemistry, we discussed basically different ways to collect a gas. One of the ways is collection over water, and the reason why we have to collect this gas over water is because H2 is a very light gas. The mass of H2O is going to be about 18, and the mass of H2 is literally 2. So it's going to be very light, and if you collect it over water, it's it's going to be very, how should I say it? It's going to be very efficient, I guess. Okay, so we can start drawing the setup. So firstly, what you're going to need to make sure in your setup is that there's no sudden holes anywhere here. So here, let's say this should not have any holes in it to show that the apparatus is sealed and no gas will escape. So what I'm drawing here is our water trough. As I mentioned earlier, it's basically a huge basin. And then we're gonna have a pipe that basically connects to a measuring cylinder, which is gonna be fixed in place or submerged here. So here, the water level is going to be a bit higher. So maybe the water level is going to be, somewhere around here. And then the gas is going to bubble up and come up there. So this is probably not the best drawing, but I think for an examiner it should suffice, and I think they should get the point to get the 2 marks. So the first mark is that it's sealed. The second is the delivery to a measuring cylinder. Okay, so next question. The surface of a magnesium ribbon has an oxide layer. This is actually one of another IGCSE concept. So basically, if you have Mg as a metal, Mg easily forms with oxygen. It easily reacts with oxygen to form MgO, which is an oxide. So on this Mg metal, you're gonna have a very thin layer of MgO. And here the question is asking how we should prepare the piece of magnesium ribbon. So obviously, if we want the reaction to be full magnesium here, then it means we have to get rid of that. And the way we get rid of that is because this layer is very thin, we can actually use sandpaper. So use sandpaper to remove oxide layer. All right. So the second part is going to be state what additional information about magnesium is required before the experiment is performed. I think probably because we know the volume of hydrochloric acid that's being used, but we do not know the mass of magnesium that's being used. So we are gonna need the mass of magnesium. And just to know, just to be sure. Okay. Show by calculation that a volume of 30 centimeter cube of half a mole per decimeter cube HCl is enough to react with 0.16 grams of magnesium ribbon. So here we can show that HCl is in excess or exactly enough. I'm not too sure, but from just looking at the question, it probably seems that it might be in excess, but we're gonna test it anyways. So I think it's best to find the mole of mg first. So that's just gonna be our mass over mr. And if I'm not mistaken, the mass of mg is 24.1. Is it? Sorry, it's 24.3. So we're gonna fix that. So in moles, we're gonna have 0.00658 moles, and the amount of HCl we need is just gonna be 2 times of that by stoichiometric ratios. So that's gonna be 0.01317 mole. So now we have to calculate the amount of HCl available, which is just 30 over 1000. This to convert times 0.5. We have a value of 30 over 1000 times 0.5. So we have 0.015 moles. So this is actually in excess. Okay. Next part is state why it is not necessary to use a burette to measure 30 cm cube of 0.50 mole dm minus 3 HCl. Okay, so basically, here in this question, it's asking why we don't have to be precise. The reason why we don't have to be precise is because this acid is already in excess. So even if we use, like a little bit under, a little bit over, again, a burette is accurate to 0.05 centimeter cube. Doesn't really matter if we have a measuring cylinder which is only accurate to 0.1 centimeter cube. The reason why it doesn't matter is because our acid is already in excess to begin with, so it's fine if we're a little bit over or a little bit under. Okay. So I'm gonna just write that down. Acid is already in excess. So highly accurate measurement is not needed. Okay. The student waits for 2 minutes before taking a reading of this volume. Suggest why the student waits 2 minutes before measuring the volume of gas in step 7. So earlier on, I did mention that it's to wait until all of the reaction is fully complete. Another reason why you would need to wait for the 2 minutes is because this is a reaction which is exothermic. So that means when you add HCl to Mg, you get a release of heat. So because you get that release of heat, it might be hotter than room temperature, and what we're trying to solve for is the molar volume at room condition. So that means we wait 2 minutes to ensure that the system is, or the setup is at room temperature. Setup and gas, actually, because what we're measuring is the gas. All right, so the next question is gonna be the student collects 146 centimeter cube of hydrogen gas during the experiment. Calculate the percentage error. All right, so here we're basically trying to find the percentage error. So that's gonna be, a physics-like question, and we're gonna have to figure that out by using the using the precision of the instrument that we used in the first place. So here the student was collecting using a 250 centimeter cube with 2 centimeter cube graduations. So with sorry, where was this? Yeah, so we're getting the percentage error. So if I think it's better if I just write the formula first. So percentage error is gonna be the delta error over real value. So we have to find the delta error here, and here our maximum error. So if we have a graduation of let's say 420, our error is gonna be the division divided by 2, so it's gonna be 1 centimeter cube. So in terms of this, our error is just gonna be plus minus 1 over 146 times 100%. So our error is gonna be plus minus 0.685%. Okay, so the next question is actually going to be on our molar volume. Here I explained earlier that it's molar mass over density of our substance. So basically, if you were to cancel out the units, this is basically just, so if you cancel this out, it's going to be the volume per mole. So molar volume is basically the volume that 1 mole of the substance takes up. And if you remember, in room conditions, it would be close to like around 24,000 centimeter cube per mole. May not always be true. That's only for an ideal gas. But we're just gonna figure out what the molar volume actually is. So basically here we actually already have a formula that we can use. So volume over mole. Our volume for the hydrogen was 146 centimeter cube, and the moles of hydrogen we had was this. So we could get the value, which is going to be that. So I think this is the last part of this question. The student's experimental value for the molar volume of hydrogen is lower than the value quoted in the table of important values, constants, and standards on page 11. So down here in page 11, we have the molar volume of gas. So yeah, as I mentioned, at room conditions, it's this. We're going to go back. Okay, so now we move on to the last part of the question. And basically, it's asking why our molar volume is less than the constant on page 11. So on page 11 here, I already marked it. Basically, the value should be this at room temperature. But our value, for some reason, is not actually that. Our job now is to determine where in the experiment we went wrong. So if you recall, here in the experiment we had our conical flask with HCl, and then we put in mg, and only after we put mg we try to stopper it, right? So even if you are very fast to stopper the flask, mg plus HCl is a very reactive reaction. So no matter how fast you are, some H2 will escape. So that's basically our answer. Some H2 will escape the moment Mg starts reacting with HCl before stoppering. And now we have to think of an improvement. And this is actually going to be a very common question in paper 5. Basically, if you need to stopper something, how are you going to make sure that no losses happen before that stoppering? So here, the problem was basically the Mg was reacting before we could stopper it. So how about we stopper the entire thing before it even has a chance to react. So let's say we have Mg here, and this is already sealed. But now we have a problem, right? Because how on earth are we gonna have HCl in our mixture? And I know this is hypocritical because earlier we said it's not necessary to use a burette, but we could actually use a burette in this situation. So if you have like a retort stand and then you clamp a burette down here. This is not the best drawing, but you get the idea. So the tip of the burette is actually going to go inside the cork, and then we could just quickly open this, and all the HCl will go in, and then it will be collected in our gas collection method, which we made earlier on. So basically, this is already sealed the moment HCl touches Mg, so we get all of the gas. How we're gonna work that is make sure reactants are already in a sealed container, but that they are separate before mixing. Alright, so that basically marks the end of question 1, and we'll be moving on to the next question. Okay, so now we move on to the second question. Basically, this time, our question is an investigation to find out how temperature affects the initial rate of decomposition of H2O2 or hydrogen peroxide. So the student already has a way to figure out how we're going to calculate this experiment, and these are basically just the details of the equipment that he's using. It's always worth giving it a quick read. In experiments 2 to 8, the solutions are heated to different temperatures before mixing and measuring the oxygen produced. The data collected is used to determine the value for the activation energy. So that means that's what we're looking for in this experiment. And yeah, I think we can just start working on this question without further ado. So the first question is state the independent variable. So in an experiment, the independent variable is basically the variable which we change. It's called independent because it is up to us to decide that variable. So usually what it would look like on a graph is the x-axis would be the independent and the y-axis would be the dependent. So if we just take a look at the graph here, we can see that on the x-axis, the independent variable has to relate to temperature, and temperature is indeed what we are able to change. So the independent variable is temperature. Okay, question B. State two variables that need to be controlled. So controlled basically just means that we need to keep constant or keep fair for all experiments. Now, I think it would be good noting what we're using in this experiment. So we're using potassium iodide, hydrogen peroxide. So again, our independent variable is only temperature, so everything else has to be constant. So what that essentially means is that the other factors affecting our experiment, like hydrogen peroxide, aqueous potassium iodide, we need to keep those constant and we need to control those. So that essentially means in here, we could either say that we need to keep the volume of H2O2 constant, we need to keep the concentration of H2O2 constant, we need to keep the volume of the catalyst constant as well. So really those are the three possible answers, I would say. So we can write that down. Volume of H2O2 used and volume of Ki used. I would also just add, for safety, at a fixed temperature. Sorry, not a fixed temperature, at a fixed concentration. All right. So, next question then. State how the student should prepare 250 centimeter cube of 0.1 mole per dm cube H2O2 from half a mole per dm cube of H2O2. So basically we're trying to dilute the solution. So from 0.5 mole per dm cube to 0.1. Now I'm gonna talk about this in two ways, I think. The first is mathematically. Let's just use, let's say, the concentration formula. Concentration is going to be equal to the number of moles per volume. So here, by diluting this solution, we're not actually, changing what's inside of the solution. So you would already have the solution in a beaker or something, or in this case, a volumetric flask. We'll get onto that later. But you already have a volumetric flask, and you have the H2O2 at 0.5 mole per dm cube. Basically, you're just gonna have to change that. So the amount of H2O2 there actually is going to be the same. It's just water or the solvent that's going to change. So that means this is actually a constant, and that would mean that our concentration is inversely proportional to the volume. Mathematically, what that means is that if we want the concentration to be 1/5, then we need to multiply the volume by 5. It's just the way it is. It's a mathematical relationship, and yeah, I think if you do physics, this would be pretty understandable. Another thing that I'd explain is to just imagine, imagine you have like 1 gram of, let's say you have 1 gram of a metal in, let's say, 10 centimeter cube of water. So right now, our concentration would be 1 gram per 0.0, okay, let's just say 1 gram per 10 centimeter cube, which equals to 0.1 gram per centimeter cube. Now, imagine you have this solution and you want to change that solution to have a concentration that's 5 times lower. So you want 0.02 grams per centimeter cube. Obviously in your beaker, you're only gonna have the 1 gram of magnesium. You just have to change the concentration. So how you do that, you're gonna have to add water. So if, let's say we had that same 1 gram, but instead we put it inside 50 centimeter cube, which is 5 times the volume, our concentration is gonna be 0.02 gram per centimeter cube. So note how the only thing we're changing here is the volume and the concentration changes. I think that's the best that I could, explain the concept behind this question. And I think we could, start getting on with it. So write your answer as a series of numbered steps. So how do we get the 0.5 to 0.1? And also use the minimum volume. So if we want 250 centimeter cube, as I mentioned, it means this volume is 5 times of the original. So it means that our original volume was 250 divided by 5, which equals to 50 centimeter cube. So what that means is that we have to measure out 50 centimeter cube of H2O2. So I would just, measure out 50 centimeter cube of H2O2 using a burette. We're using a burette here because in this case, for this experiment, we want to be as accurate as possible. And transfer to a volumetric flask. Now, at this point, you might be thinking, why are we using a volumetric flask? Why can't we use a beaker or a conical flask? The thing again is that we want to be precise. Our measuring cylinders and our conical flasks are somewhat accurate, but not really. They just give a very rough idea of what's inside our container. But a volumetric flask, which looks like this, it's gonna have a very long stem, and it's gonna have a marking, somewhere around here. Let's say if it's calibrated to 250 centimeter cube, this marking is gonna be very, very accurate. So anytime in a paper 5 question where you're asked to make a new solution, change the concentration, something like that, you're gonna use a volumetric flask. So a volumetric flask is what you use to make solutions. It's very handy to remember that. And the reason is because it's very accurate. Again, that explains the first step. So the second step is, we already have that 50 centimeter cube. What we're gonna do is we're gonna top up the flask with water up to the 250 centimeter cube mark. So as I mentioned again, there's gonna be a mark here. So if, let's say, we had H2O2 until that level, we're gonna add water all the way until it's filled up to that line. That's how we know it's already at a perfect 250 centimeter cube. So yeah, I guess that's it for that question. Hydrogen peroxide causes eye and skin irritation. State what precautions should be taken when preparing the solution in CI other than wearing goggles. Okay, so goggles is to address the eyes, so now we have to address the skin irritation. Obviously, if you want to, remove skin irritation, then you'd have to wear gloves. But that's not the end of it, because there's lots of types of gloves on the market. I actually have a story with this. When I was doing an experiment using, I think it was dimethyl ether, something like that, I forgot. Basically what happened was the gloves I were wearing were very thin and they were not chemically resistant. So what happened was it still penetrated into my skin and it burned pretty bad. So even if you're wearing gloves, that gives you a layer of protection, but those gloves really have to be chemically resistant. So use chemically resistant gloves. All right. So next we're gonna move on to the next question. So, as you can see, I've already did a bit of calculation there, but we're just gonna restart this. Basically, all you're gonna do here for this column is we're just gonna do 1 over the temperature given here. So we're gonna do 1 over 293 here, for example, which gives us a value of 0.00341. On your calculator, you're going to get a different value from this, but you're going to round it up to 3 significant figures. The reason for that is because everything here in your graph is given in 3 significant figures. So even if you go more accurate than that, it's not going to really help you because it's not going to help you plot out the graph. So again, I've already calculated this beforehand to save time. So I'm just going to plot down what I have. All right. For the next one, we're gonna do log initial rate. Please do note that this is log 10, log base 10. But on your calculator, if you just write log, it should do the trick. So again, an example would be this. And that's gonna give us minus 5.24. Again, I would round it up to 3 significant figures because our graph is going to be accurate up until the second decimal place. So I would also round it up to the second decimal place here. Again, I've already calculated this as well, and we're just going to plug that in. Minus 4.43, minus 4.28, and minus 4.20. All right, so now we're gonna have to plot the graph. Use a cross to plot each point. The reason you use a cross is because it's way more accurate than doing a dot. Because some people, when they make the dot, it's super thick and it's unclear. But with X, you can see the exact point where it lands. So yeah, we're just gonna plot that out. Again, I would be very careful with this. The reason is because if you mess up on a point, it could mess up your whole graph and it's going to be very weird. We don't want that. So plot each data point one by one. So we're going to find negative 5.24, which is going to be here. And we're going to find 0.00341, which is this is 0.00345. So 341 must be this point. So I'm just gonna plot that over here. Again, I want to be very thin with these crosses. Next one is minus 5.10. That's gonna be over here on a nice thick line. And then we're gonna find 0.336, which is gonna be here. So it's gonna be on this line. There we go. Some very small crosses again. Just to be very precise. 4.93 is gonna be, where is 4.93? This is 4.93 over here. Oh, yeah, 4.93 is gonna be there. And our point is gonna be at 0.0030. So that's gonna be a nice point around here. And then 0.00325 is going to be on this with minus 4.84. So that's going to be around here. Again, try to be as precise as you can. Next is going to be 321, 4.66, 4.66. So 321 is going to be here. 4.66 is going to be... Where is 4.66? It's gonna be here. Again, make sure to take time with this, and on the actual exam paper, you are allowed to write with pencil. So I would do it with a HB pencil, just because if you mess up, it's gonna be much easier to erase. So this is 4.43. 0.00313 is gonna be here. So it's gonna be the 6th line. Okay, there we go. Just a couple more. 3.08 is gonna be here, and 4.28 is gonna be here. One more point, 4.20. It's gonna be right on our edge, and the time is gonna be 3:05. So right here, perfect. Yep, that's about perfect. Now we have to draw a line of best fit. Let me see if I can find a ruler around here. Okay, I can't find a ruler. That's the best thing that we're gonna have for a ruler. So I'm just gonna delete that. And let's just take this to be our ruler. Basically what you're trying to do here is you're gonna have to draw the line of best fit. Honestly, wait, hold on. Let me just make a better ruler than that. Okay, so imagine that this is our ruler and we're gonna draw a line of best fit. Actually, let me check if the question, yep, draw a line of best fit. So a line of best fit is gonna try to balance among the points. So as much as possible, how many data points do you have here? You have 8 data points. So you have 1, 2, 3, 4, 5, 6, 7, 8. So as much as possible, you want to have 4 points above your graph, above your ruler, and you're gonna want 3 under. So in this case, if we draw a line sort of like that, maybe a little bit more like that to compensate. Okay, something around that. If we draw a line straight through here, let's see if that's gonna be straight. Yep. Maybe this isn't the best line, but they are, I think, quite lenient with it. So here, 1, 2, 3, 4 points are above the line. Here, 1, 2, 3, 4 points are above the line. Maybe I'd shift this line just a bit here, just to get the bottom points closer. And this line looks pretty balanced to me. So you have 4 points above, 4 points below. Looks pretty good to me, and that looks like a line of best fit. So now we have to circle the point on the graph which we feel is most anomalous. I think even here from our graph, we could tell that there's a deviation. The reason is because, hold on, where was it? This 5, 6, 5, 5. From here to here, from the 5th to the 6th point, it seems that there's a bigger jump than expected. So between 5 and 6. So point number 6 is going to be at 313. So 313 is going to be here. And that could be an anomalous point on our graph. It could also be this point here at 325. Yeah, those could be the points. Personally, on this best fit graph, I would probably pick this one, because if you notice, you could draw a line kind of like that and it would go very straight, but this seems to drag it down. The reason why it's probably being dragged down is because it's being offset too much to the left, and the reason for that is because the temperature is the temperature is bigger than it actually was. The recorded temperature was bigger, so that shifts its value to the left because it's now smaller. So that's actually going to be our answer, I think. That's our anomalous point, and we're going to say it shifted left because recorded temperature was higher than actual temp. All right, so next we're going to determine the gradient. So how you're going to do a gradient is you're going to draw a triangle on your graph. So you can take any point which you want on the graph. As much as possible, try to use a big area on the graph. So if you see what I'm doing here, my points are, my triangle is pretty big. It's taking up more than half of the triangle. So yeah, so this is going to be my first coordinate, this is going to be my second coordinate, and we're going to write that down. So this one is going to be 0.00310 negative, what is that, 4.4? 4.4. And this one is going to be 0.00338 and minus 5.1. So the formula for gradient is as follows, which is going to be 0.00310 minus 0.00338 over minus 4.4 minus 5.1. So our gradient, if we plug it into the calculator, is going to be oh wow, I'm getting a very high gradient. I got negative 2,500. That's on the dot, by the way, exactly negative 2,500. All right, so we're gonna use the next question. Also just a tip, if you're unsure about your value, try to make sure with this, because they say if you're unable to obtain the value, you can use this value. If the amount of, if like, let's say your value was 200 and this is the value they give, it's probably wrong. If it was like 3,200 or like 2,900, it's probably correct, because it's in thousands as well. So that's really how you try to verify your answer. Okay, so basically here, you might see this complex equation, but it's actually really simple. If you can recall, our log initial rate was our y value. Our intercept is somewhere around here. So that's going to be our intercept. And this is going to be our gradient. So to make it clearer, I'll rewrite this. EA over 2.303 r times 1 over t. And remember, our 1 over t is our x value. So it means this is our gradient, m. So our EA equals to our EA over 2.303 r equals to m. So that means our m is going to be, our EA is going to be 2.303 times r times m. So if we're going to find the value of r, it's 8.31. So 8.31 times 2.303 times our gradient, negative 2,500. That's going to be 8.31 times 2.303. This is not going to be negative actually. Why is it not negative? because our gradient is actually, apologize for the mistake here, our gradient is minus EA. So I'm gonna add a minus there. So times minus 2500. Basically the minuses cancel out there. So yeah, our value is gonna be 47,845 joules. The reason why it's joules, our gas constant is in joules, so this is going to be in joules as well. If we want to round it off, we just divide by 1,000, so it's going to be 47.8 kilojoules. It is not possible to repeat the investigation. Do you think the data from this investigation is reliable? Basically, it's asking, can you draw a valid conclusion from this graph? And I would say no. The reason, because there's an anomalous data point. Even if just one of your data points is off, that's gonna mess up the graph, especially when you only have 8 different data points. So this one point already messes up our graph, because if hypothetically we were to cover up that point, then our line of best fit would be, you know, somewhere along there. So those are very different lines. So I would say no. There is an anomalous data point which skews our graph. I think that's about it for this paper. Paper 5 can be a little bit tricky if you don't practice. I myself wouldn't consider myself the best at paper 5 either, but really here in this question especially, you really have to imagine like you were actually doing this in a lab. Here in the data analysis point, if you do physics, it might really help this part as well. But for these types of questions, you know, II, BA, CI especially, you really need to imagine yourself in the lab doing the experiment. So if any of you are watching and still doing AS when you're doing your lab work, please do, you know, slow down a little when you're practicing, and, you know, appreciate the equipment around you and really understand what it's being used for. I think that's all I have to offer for this video, and I really hope that my explanations were helpful. Thank you very much for watching, and I'll see you again in another video.